Welcome to the deployment of Asphalt Pavement Technologies webinar series on the 8 tasks toward the implementation of balanced mix design for asphalt mixtures. The Federal Highway Administration has an ongoing accelerated implementation and deployment of pavement technologies program, which includes deployment of innovative technologies to improve pavement performance and reduce the agency risk. This presentation was prepared by Eli Hash from University of Nevada, Reno, Tim Aschenbrenner, and Derek Nenner-Plante from the Federal Highway Administration under the Development and Deployment of Innovative Asphalt Pavement Technologies Cooperative Agreement with the University of Nevada, Reno. The material is disseminated under the sponsorship of the U.S. Department of Transportation in the interest of information exchange under the cooperative agreement listed. The U.S. government assumes no liability for the use of the information contained in this presentation. The U.S. government does not endorse products or manufacturers or outside entities. Trademarks, names, or logos appear in this presentation only because they are considered essential to the objective of the document. They are included for informational purposes only and are not intended to reflect a preference, approval, or endorsement of any one product or entity. This presentation is arranged into 4 sections corresponding to the major headings of the companion tech brief on balanced asphalt mix design, 8 tasks for implementations. Section 1 presents a brief introduction, followed by definitions information in Section 2. Section 3, tasks for BMD implementation, discuss the 8 potential tasks for implementation of balanced mix design, and we will have some conclusions and a summary in Section 4. Virtual site visits were conducted with 7 state DOTs to identify positive practices, lessons learned, and challenges when implementing BMD and mechanical testing of asphalt mixtures. Each site visit included a pre-visit kickoff meeting and a 2 to 4 day virtual site visit to obtain detailed understanding of agency practices and lessons learned that can facilitate the implementation of a BMD program into a practice at other state DOTs. This included interviews with agency personnel, contractors, and academia. A report on the observations and practices identified was prepared and shared with each FHWA division office and state DOT visited. An overall summary report and a tech brief were also developed. The 7 state DOT reports, the overall summary reports, as well as a tech brief can be found at the listed website links and the QR code shown on this slide. The expected outcome of this webinar are to understand the why, the motivation, and overall benefits of balanced mix design, recognize the overall planning and coordination effort associated with the implementation process of balanced mix design, identify the tasks that needs to be completed for the development and implementation of BMD, recognize successful key state DOT practices and experiences related to balanced mix design, and recognize available external technical information and support. What would not be covered in the webinar are things related to how to perform BMD tests, what is the best test parameters, research results, and so forth. Next, we will be going over a few definitions. Starting first with the definition of what is a BMD. According to the AASHTO PP 105 and to the glossary of terms for balanced design of asphalt mixtures, a BMD is an asphalt mix design framework using mechanical tests correlated to field performance on appropriately conditioned specimens that address multiple modes of asphalt layer distress while taking into consideration the asphalt mixture aging, the traffic, the climate, and the location within the pavement structure. So it is a design philosophy that is used to optimize the asphalt mixture performance against the distresses pertinent to the climate and traffic speed to the region where the asphalt mixture will be placed. Let's start by looking into the current standard, the volumetric base mix design. So whether the mix design is developed through a Marshall, Veeam, or SuperPave mix design process, there are basic volumetric requirements that the asphalt mixture must be designed to meet. Each of air voids, voids in mineral aggregates, voids filled with asphalt must fall within a specific range in order to have a successful asphalt mix design. So the current standard is we select a design air void, and at that design air void we come up with the optimum asphalt binder content, and then we make sure that at the optimum asphalt binder contents we meet other volumetric requirements such as the voids in mineral aggregates and the voids filled with asphalt. If that is not the case, then we're going to have to go back and make adjustments to our blend aggregate gradations. Now, what about the balanced mix design? The initial concept of balanced mix design was how can we get more asphalt binders into our asphalt mixtures so that we can assure proper durability and longevity of our asphalt materials. So if we're looking here at two properties, the two major type of distresses that are currently being looked at is cracking and rotting. So on the left hand side you see your cracking resistance, and on the right hand side you see your rotting resistance. The optimum volumetric optimum asphalt binder content is basically what you get out of your volumetric based mix design. So if we start changing the asphalt binder content, we expect that the cracking resistance to increase with the increase of the asphalt binder, whereas we expect that the rotting resistance decrease with the increase of the asphalt binder content. So if we set a minimum threshold value for our cracking resistance, then we can come up with the minimum asphalt binder content to get an acceptable cracking resistance. But at the same time, we don't want to jeopardize rotting resistance, so there will be a maximum value for the asphalt binder content set by limiting the rotting properties. That will give us a range of asphalt binder contents where I can meet both cracking and rotting resistance. And this is where that balanced optimum come into a play, where I can shift my asphalt binder content so I can have enough binder in my mix to improve cracking resistance, but making sure that I don't jeopardize the rotting resistance of the asphalt mixtures. While this was the initial concept of the BMD, where the focus was how I can add more asphalt binder content to my mix so I can balance these two different type of distresses. Well, we find out that in reality, that's not how we are doing balanced mix designs. Actually, as an example, we're showing over here what we call a mechanical testing diagram for the balanced mix design, where on the y-axis now we're seeing the first property, like the cracking resistance, and on the x-axis now we're seeing the rotting resistance. So going back to the same principle that we need to achieve a minimum cracking resistance, and we need to achieve a minimum rotting resistance. So what you're seeing over here, the green area, is where I really want to be, where I have an acceptable cracking and acceptable rotting resistance. The red, what you see over here, where you don't want to be there because obviously you're failing both cracking and rotting. The yellow zones is where you're passing one property but failing the other property. So when you come up with your volumetric mix design and you end up, in the yellow zone over here, for example, this is your X. The question now become, as a mix designer, what kind of changes I can make so I can move that X into the green zones. Now, there are multiple changes that I can do, or adjustments that I can do for my mixes. Yes, it could be by adding asphalt binder content. I can be able to meet that without jeopardizing rotting. But what we find out, there are other ways into moving that X into the green circle, which could be by altering the aggregate gradation so I can have more effective asphalt binder in my mix, using a different asphalt binder grade, different PG grade, or changing the asphalt binder source without necessarily changing the PG of the asphalt binder. So there are multiple strategies available to achieve an acceptable performance. So within the balanced mix design framework, there are 4 primary approaches, A through D, for the mix design. The differences between the approaches are really highlighted in the presented table in terms of volumetric requirements, mixture mechanical testing requirements, the flexibility of the approach, and the innovation potential. Approach A is the most conservative with the lowest innovation potential, while approach D is the least conservative with the highest degree of innovation potential. These approaches are being implemented and explored by a number of state DOTs to address concerns about pavement performance with the traditional volumetric mixed design methods. Most of the state agencies are starting with approach A until they gain enough confidence in the mechanical test so they can start moving into the approach B, C, and hopefully at one point into approach D. Our next section focuses on the potential 8 tasks for the implementation of balanced mixed design. So successful practices documented from these 7 virtual site visits were all collected and synthesized into an overall process of implementation of BMD. This effort suggested 8 major tasks based on concurrent activities such as the BMD regional workshops, the BMD implementation guide, and so forth. These tasks summarize the activities that an agency may need to undertake, and not all tasks may be applied or considered depending on the state organizational structure, staffing level, workspace, the annual asphalt tonnage, as well as industry experiences and practices. Several tasks may be conducted in parallel or in a different order. In this webinar, select example from the visited states under each of the 8 tasks are being presented. So the first task focuses on making sure stakeholders understand why a new approach to mixed design acceptance is needed and the benefits expected with a change. The why, the motivation may be different for different state DOTs. Here's a summary for the visited state DOT's motivations. Overall, all 7 states were looking into improving pavement performance, like raveling, durability, and cracking are most premature failures observed, even though adjustments were made to the current superpave volumetric base mix design, such as by changing gyration levels, adjusting the volumetric property requirements. While there were some improvement with those adjustments, but they were not enough to address all the challenges and the problem that these state DOTs are facing. Example of state DOT benefits are listed on the slides and includes testimony of the benefits of implementing the mechanical tests, fewer cases of premature failure resulting in cost savings, to overall improvement of the road network. An example illustrating the benefit observed by New Jersey Department of Transportation from using specialty asphalt mixtures following the BMD is presented. An overall improvement in the condition of the state DOT pavement network is observed. The percent system lane miles in good condition increased in 13 years from 12% to 40% since the implementation of the specialty mixtures with performance testing. Moving on into task 2, which is concerned with understanding the overall implementation process for balanced mix design, defining and setting the goals, as well as determining the resources necessary to achieve those goals within a realistic timeline. I will hand it over to Derek Nenner-Plenty to cover task 2.
Thanks, Ellie. I'll continue with the topic of task 2, and that's where we get into overall planning for BMD implementation. So, as Ellie talked about, understanding why you're doing this is important. Now, let's make a plan, right? First couple things that you want to think about as you get started with making a plan that we've seen from those states that we talked to is champions. Much like any change at a state DOT level that we've seen in asphalt and other areas, it requires a champion. So what kind of activities did they do? We saw examples of getting upper level management buy-in and leadership support and the commitment for resources that may be necessary to make the implementation happen, be it research, lab space, people, etc. Within, we also had an example from New Jersey where they had an internal partnership. That this often, BMD implementation, will go beyond just one part of a state DOT, be it materials or construction, pavement design. So they had to establish an internal partnership between materials mix design and management to really make it happen. And then beyond that, not just support at the state DOT level, but to get to some sort of task force or stakeholder community to work agency, industry, and academia as suitable. So Illinois, we saw the use of an implementation task force. In Virginia, we see the use of actually two different levels of stakeholder partnership, where they have a BMD task force that's kind of the parent to it, managers, etc., that are looking at the overall implementation implications. But then they have a technical subcommittee that dives a little bit more into the technical details. So if you're going to get into a large discussion about ideal CT variability and specimen fabrication, most likely it's going to be at a technical subcommittee level, whereas overall direction, maybe the why, the overall planning, comes at that parent task force. But as with many things, stakeholder partnership has got to happen in order to put this change in and have it be effective for everyone. Another part of task 2 in this overall planning is doing your homework. So we found a lot of these states did their homework as they got into BMD. So what does that mean, doing your homework? A couple things that we saw commonly here were, first, identify what your issues are. Okay, what's the performance that you're trying to change, or what's your goals? Okay, I'm gonna hit on that in a second. But know what you're currently getting for performance. What are you getting for that's driving the performance of your mixtures, and how do they perform across your different categories? Identifying resources. What's available to you to make BMD happen? All right, look at your organizational structure. How could you change things, etc.? What does your program look like today? And then finally, review the literature. Everyone seems to be working on BMD and quote-unquote performance tests. Review that for the tests that you're looking at. Maybe look at what you've done historically. Okay, having the knowledge of what other state DOTs, maybe primarily in your region, are doing, and enhance knowledge exchange, which is part of why things like peer exchanges that Federal Highway is trying to do and others is really important, to know what others are doing. We don't need to repeat all the work that others are doing out there. Huge part of task 2 is establishing goals. What do you want to get out of moving to BMD? Change requires effort. What is it? What are you going to get out of it? Understanding what's the why for your situation. And then what is it going to look like? Okay, so the goals are defined with considerations for the differences that we have among different agencies across the country. There's different organizational structure, the size of their program, industry experience, certainly things like climate, but even beyond that, how is paving done there? It's done very differently in parts of the country where they have more portable plants versus others where they're more permanent setups. Okay, the scope for BMD program and how they use it into projects varies, and primarily the major things that we see change there is mixture quantity and roadway corridor classification for how they might use BMD. How much mix is going on projects and where are the projects? So you can see, as far as goals, all right, to the right here of the table of the agencies that we looked at, asked to try and categorize, and you see a wide range of, we see some states that went and wanted it to be on all mixes. All right, all projects, all mixes. Now they used a phased approach, but their end goal was to put it everywhere for design and into acceptance and production. Whereas other agencies looked at, our goal is just design right now, or it's just this category of work, often the highest priority work. So having those goals, what we like to say, what does BMD look like? If it's implemented in a couple years, What does it look like in your situation? And the thing you also need to think about is how is this, it can result in many different levels of changes. BMD is not a one size fits all approach. So these are just some examples of questions to think about. You don't need to have the answer to all of them. And it's not like the answer won't change as you're going through implementation. But these are the things to be thinking about. Who's going to do the mixed design and testing? Is it going to be both industry and state DOT? All right. How to plan for that additional workload, cost. How is the state DOT going to verify mixed designs if BMD? Is that going to change from what they're currently doing? How is production testing going to get done? BMD kind of implies that it's going to be done at mixed design, right? Balanced mixed design. But balanced mixed design can also be brought into the production environment. Is that part of the goal right away, or is that longer down? How will dispute resolution be handled if something fails? How is that going to be handled? Do people have the skilled workforce necessary? These are just a sampling of the questions to think about to really have a common understanding, I guess, of a group that's looking to implement BMD, which would be an agency and industry together. What does BMD look like in your state? Again, it may change over time. That's fine. But at least that vision of what it looks like might be shared. And then finally, we talk about developing an implementation timeline. Think about all this task 2 is setting out a plan, all right? And some would say the plan is when deviations begin, right? That goes to the timeline as well, all right? As soon as you print the schedule, it's out of date, right? But still, the process of setting a timeline helps in getting things moving. So many of the agencies that we talk to, set timelines. With that, it allows them to consider the resources necessary. If you have an indefinite time, then resources don't come in as much. Whereas if you have a goal to hit something and get something complete by a certain date, you need to consider the resources to get that done. It also helps to define the scope. It's not just BMD in general, but what does BMD look like? And have major milestones. So just as an example, Illinois is a state that is now fully implemented with BMD, and this was an initial schedule that they had put out there when we talked to them. They had some of the original research, and that they would finish the research in 2016 and have machines online soon thereafter. Okay, now they can shift, right? These timelines can shift, but having that target is important. So to show how they shift, here is a documentation of where Illinois was with the IFIT. Now, mind you, you can see that this spans 9 to 10 years. This test was developed, right? It wasn't a test that was already made at this point. Okay, but you see the progression. And a big thing to note here is that they had progression each year. You don't see kind of stagnating over a period of time. Certainly, did it take it longer than they anticipated? Of course. But they had major milestones that even when they got pulled back or pushed back a bit, they still had those milestones and they had a goal. So having a timeline goal is important, especially when thinking about resources. All right, so that's task 2 in overall planning, kind of setting the road out ahead of you. Now, let's start getting some stuff done. And that brings in task 3, which is selecting performance tests. And we have 3 subtasks here that we talk about. Now, task 3 can take a long time. We have some very important things to think about in task 3. First one is, what distresses am I worried about? Ellie talked about the BMD definition earlier, okay, that it's trying to prevent the distresses, but the distresses may be different for each person that's listening to this, for each state, right? Certainly different in the northern and the southern parts of the country. So identify what are your primary modes of distress that drive pavement performance in your situation. Now you want to match candidate performance tests that are good candidates based upon the existing literature and work that's out there to those distresses. And then assess those tests for how they might be routinely used in your kind of BMD goal and scope that you've thought about. So there's a lot of things to think about here, not just the tests. Sample preparation, conditioning, and testing are often even more important than the testing itself. How to get to a sample, how long does it take to get to a sample? What are the training needs, equipment cost, variability and repeatability, sensitivity of materials, and then kind of the golden thing, field validation, okay? Considerations to asphalt mixture acceptance during production, okay? There are many different ways to do that. All right, so that does come into when thinking about the test, because there are many ways to think about how you might bring BMD into acceptance. Maybe you do this test, or maybe it's different than the one you do at mixed design. That's kind of a surrogate approach that's correlated to maybe a more complicated test at mixed design, but then there's a more rapid one that you do in production. So thinking about that is important. All right, as an example here, we have kind of assessing some rutting results from a New England area transportation project that looked at different traffic levels and how much field rutting they saw time over construction. So what did they want? What was their goal? What was the mode of the stress that they were trying to design against? A big consideration is test variability. We've tried to synthesize a lot of the work that's been out there on the different cracking tests and the coefficient of variation, or COV. Often variability is found to be most of concern in the cracking test realm and less so in the rutting tests. There's a lot more variability and intricacies to that testing, often stiffness based, and there are many things that can affect that, often specimen preparation. But you see the COVs are an important thing here, because the higher variability, the harder it is to distinguish between two different results and say, is this 40 and this 50? Are they truly different? Or given the variability of the test, I can't discern that they are truly different. Okay, good resource there is the link at the Napa BMD resource guide that talks about these and gives more information on the variability of the test, but it has to be a consideration for thinking about what test is going to work for you. We did talk to those state DOTs that we worked with as part of the case studies and talked about their top 3 factors, right? What were their top 3 factors to selecting the test that they looked at? And you see the responses here, and you see some overlap between many of them, and also some differences. Okay, so things from specimen preparation, equipment cost. Equipment cost didn't really come in for many. Training needs and applicability wasn't talked about for many. Often variability. There were some agencies that really focused in on sensitivity, variability, and validation. Okay. Others looked at, we can't do anything unless it's something that we can do the specimen prep and conditioning easily. And you see the example from New Jersey that shows that they looked at it differently from design and verification, so that mixed design phase, to acceptance. And their priorities changed, okay, between the two. And that's where the surrogate approach I talked about comes in. And the idea that New Jersey and Texas, as examples, are looking into is that, is there a test that they could do at mixed design that might take more time, right? Its specimen preparation is more laborious. Maybe the equipment even costs more, slightly more complicated. And they do that in mixed design when maybe time is less critical. But they use a surrogate in production to try and predict that result. So this is a figure example from Texas that really believes in the overlay test for cracking and the Hamburg wheel tracker. Now, both of those tests take time. The ideal CT and the ideal RT are tests that are a bit more rapid. Okay, so what they're thinking about is establishing a correlation by mix in between the tests, and then in production and acceptance, running the ideal CT and ideal RT to diagnose if issues are out there. So the thinking about the test may change depending on how you're going to use it. And then finally in task 3, the major thing here, and it's so major with BMD, is to make sure that whatever these mechanical or performance test results give you, that they have a strong relationship to actual field performance. And why is this important? This is important because when you go to pick a number, criteria development, what's going to be the difference between passing and failing? maybe if I bring it to acceptance between full pay and disincentive down the line. But what is that number going to be? It's critical for that. It needs to be defendable, right? It needs to have a work behind it that says that whatever the number is, it's defensible, right? So that that criteria was developed in some way that relates back to field performance. Anything can be called a performance test. We have many tests. They'll be called performance tests at the time, and maybe they're not called that anymore because we believe we have better tools that better predict field performance. And BMD should be a move down that line to better predict field performance. But we still need to establish that for the mixes that we have. So we got to confirm that relationship in order to develop criteria. This is very different than benchmarking. I'll talk about that in a little bit. Benchmarking is about what you're getting now, but what do I need is validation, and that's this task 3 item. So an example just from Texas as how they looked at validating their performance tests. They had a historical database of test results and were able to associate that over to field performance for Hamburg and overlay tests for an array of different mixtures. So what they did was they compared with that research to field performance, of which we have a paper cited here, and then continued adding to an ongoing database where they've been able to improve analysis methods and update criteria as they get new results. You'll see this as a feedback loop and keep that in mind. So additional validation studies have been done at accelerated loading facilities, NCAT test sections, and they're placing more field test sections to continue to validate that criteria, that the relationship that they have established historically continues. So having that large database of test results for typical mixtures was key. The key thing here is their respective history of field performance. It's very easy to test a mix now. The harder thing is to get that field performance because it takes time. So anything that you can do that is in back, and there's many different ways to establish that. There's not one right way to establish that relationship. We have many resources at the publications that we reference that talk about that. All right, next task for BMD implementation that we'll talk about is task 4, where we're talking about the equipment and resources. So in task 4, we talk about a number of kind of real world things as we're getting our hands dirty and getting started. So in here, we talk about acquiring equipment. And that's going to be different for the contractor and the agencies. Maybe different for central labs versus district labs. Do I modify existing load frames? Do I get something new? The challenges were different for all those that we talked to, but acquiring equipment was not something that was easy like that. Workspace labs. There aren't too many labs that we go to that have all this ample extra space. So often there were efforts to rearrange labs to have space for this to be a priority. We had those that had to reorganize or repurpose laundry rooms to fit equipment or convert a stairwell to house new equipment as well. On the staffing or resources side, we had those that had to consider current staffing and equipment and think about repurposing them or getting new resources. Specimen fabrication is obviously a big thing with BMD. So it may not just be the equipment, but oven space, gyratories, etc. to feed these machines. It's something to think about how to meet the need of the testing that will need to implement BMD, but also the time to transition. So there might be a bump in resource level needs before any gains can be made. Some agencies we talked to had to hire dedicated staff, that this wasn't something somebody could just do part-time, that they needed dedicated staff to do this. And we had an example from Texas where they had a material producer list of labs, of consultant labs that could help perform the Hamburg, because otherwise they wouldn't be able to handle the workload. So they went outside to consultants to help meet that need. Then something about task 4 that's common to all that we found value in is evaluating those performance tests once you start doing them. It's one thing to read a paper about it. Now you're getting your hands dirty. You're doing it yourself. So evaluate that performance test and think about interlaboratory studies. So some examples here. Illinois used interlaboratory studies to help develop their long-term aging protocol for lab-produced and plant-produced specimens, where they landed at 72 hours for 95C. This was where they had to perform a lot of testing on their own or investigation on their own to come up with that procedure. Louisiana is looking at an SCB aging scaling factor to estimate test results at an aged condition. Again, they're evaluating the test by looking at this. New Jersey looked at lab-produced versus plant-produced mixes, where they found in some cases plant-produced mixes were failing potential criteria but performing well in the field. So they ended up actually relaxing some criteria based upon that, but it's all kind of this, I would characterize it almost as a natural curiosity with a new test. What matters here? What makes a difference, etc. And then finally, interlaboratory studies was common to everyone we've talked to in this case as a really successful practice. It helps, just like any other test that we try and put into practice, it helps to refine the test procedure, drive out variabilities, refine not only test procedure but fabrication, which has just as much or more testing variability impact, and then keeping uniform. We want everybody to be running the test the same way with new and existing labs. All right, moving on to task 5, which is establishing baseline data. This one is one where many agencies are at now, and again, it takes time. Here we're collecting information. We're going to collect our information to make some big decisions later on. So, one big thing that I need to clarify before moving on here is I've used the term validation and I've used the term benchmarking, which we'll talk about here in task 5. How are they different? Because we've seen a lot of confusion between the two. Validation, when talking about BMD, is when we're trying to make sure that whatever tests we have, those results have a strong relationship to field performance, because field performance is what matters. So we want to have a pretty good relationship with field performance. Why do we need that? Because we need that to develop specification criteria and to make sure that the test is an improvement upon what we've already got. Now that's different than benchmarking. When we benchmark, we're taking our existing mixes, right, and see how they perform in a new test. We're taking maybe products in a certain category that are being given all in the same category and see how they perform in this new test. It helps you to know what you got now, what might need to change if a new test comes along and a new criteria comes along. But benchmarking alone doesn't get you criteria, because then you're not changing anything. All right, first thing that we talk about in task 5 as far as things to consider is just look at data that you have. If you have any historical data, either on testing data or performance data, be it performance in the field, it can be useful. You've already got it. Okay, so we have an example here from Louisiana that they had a long record of test results, and it really accelerated their validation or criteria development effort, as you can see here, where they established their initial criteria off of all this historical data. And they were able to place new sections, place new mixes to further validate this effort. So use the data you have. Even if you can't go back and run the new tests on mixes from previous, maybe you can try and replicate it. Maybe you know what mixes are historically behaving well and not behaving well out in the field. That will still help you. So within task 5, we talk about benchmarking. And benchmarking is a major part of task 5. See where you're at, and this is something that many agencies are looking at. So this is an example from Illinois that's been looking at the iFit for a long time now, which produces the flexibility index. So this was, at the time, they had over 3,000 test sets of results across mixes that they were currently getting supplied for their specification over a number of different mix types. And there are many things that you can do with this data. You can look at this data to evaluate your proposed criteria, right? How many mixes would require adjustment if this were the criteria today? What are the trends in the different type of mixes? And these are some of the analysis that they were able to do. They looked at volumetric properties, or things that they would expect, that everything else being equal, that more asphalt would lead to better flexibility index. And you see that in the top right. Okay, that a lower PG temperature would get you better results. That more recycled binder might lower flexibility index. Or that more voids in the mineral aggregate would lead to more effective binder and a higher flexibility index. So this gained confidence for them, that they saw trends that overall, that what they expected to happen was reflected in this. But the big thing is that this was information that also could be available to their contractors in their industry to see, again, what would need to change from what they're doing right now. Helps evaluate criteria that's developed through validation, helps to see the contractors that might need to adjust something to move forward, helps to see what things matter when put up against a new test. Just like we did with SuperPave, you know, we like to joke that there's no voids in the mineral aggregate VMA button in the plant to turn that up, right? Everyone had to get used to how adjust to get to VMA. Well, benchmarking can help provide that data that shows what really matters for a given BMD test, what things to pay attention to. And that's just some of the value that benchmarking provides. A big thing that you have to acknowledge here is that in order to do something like what you see here is to have a database. And Illinois had a database that they entered benchmarking results into in order to find this all and use this data so that they could look up a given mix and see how it's performing in these tests, or run the data to see how it relates between total asphalt content and flexibility index. So having a well thought out plan for how to house this data so you can analyze it easier later on is really important. Another example we have is from Maine DOT. They have a database that they've been able to compare results of tests from splits of acceptance samples, and they've compared it to volumetric properties on those same samples. And what they're showing here is 4 of their major type of mixes, 12.5 and 9.5 nominal maximum aggregate sizes, with and without polymer modified binder. And you see, although the numbers for each category in the 20s for mixes, they can still start looking at this data. And they have a mean standard deviation COV of the different mixes. But what's really helpful is on the right, like you see, the cumulative distribution chart. So it's showing that if you think of each one of those lines as a given category or product, it's a nominal maximum aggregate size, it's a certain PG binder, that's being supplied as an equivalent product. And what they're seeing is vast changes in CT index among mixes that they get. And if you just look at that red line as an example, you're seeing the differences between these different categories. So they're seeing an expected bump in performance from polymer in this case and from the finer gradations. But you can also see the spread. You can see the spread in the performance of the mixes in that one category. Some might look at that and say, oh, that's not good. To me, in my perspective, that's good. This test is catching something that we're not catching in our existing other specifications. These are all equivalent mixes per the specification. And if we believe that BMD is going to catch something that we're not currently, this is at least showing that. Conducting shadow projects is a big part of task 5 beyond benchmarking, and this is when you bring it out into the field. These shadow projects are when you do projects where the test results are purely informational. It's to gain familiarity with the selected tests, add to your benchmarking database, but a big thing that you have to do here is understand production variability. If part of your goals and scope are to bring this to production, this is necessary, all right? So, things that people have learned through shadow projects is they've had to think about turnaround time. It's all well and fine when it's in a research lab somewhere, but now if you're trying to keep up with project production, boy, we got to think about how we got to do this. So prioritization, oven space, water bath space, maybe technician time. How are we going to do that if we bring this to the pilot stage? They found challenges with dealing with more than one project at a time, getting the samples from the contractor promptly, and what happens when it fails. Again, all these test results are information. It's a chance to play pretend with this. What would happen? And figure out some of the logistics with bringing BMD to the field before you get to a pilot project. Just something to think about with these careful selection of the projects is key. You want to make sure it's the right type of project. It's not going to hinder production or impact the contractor negatively anyway. And you also need to start thinking about careful documentation, because you'll have BMD test results. You'll want to compare it to field performance in a couple of years. So if something goes wrong in construction, you want to have that well documented. And then finally in task 5, it's time to start thinking about adjusting mixes, especially from the contractors that are listening, right? If my mix is not performing well in these BMD tests, how do I change it? We found, talking to contractors around the country and some of the work that we've done, adjustments are often material specific. We know that, right? Not all aggregates are the same, not all binders are the same, all right? Binder selection is based upon stiffness often, and not just meeting PG. Often, what we've seen is getting back to the basics here, paying attention to gradation and bin adjustments to make more effective binder. Maybe our total binder doesn't need to go up, but maybe our effective binder can be made to go up by getting more voids in the mineral aggregate, more effective binder in the mix. All right. Often we've heard about minimization of natural sand, especially issues with maybe the Hamburg wheel tracker, thinking about wrap a little bit more and consistency in the wrap feed and differences between the different types of gradation. So all these kind of things, they're really more of a back to basics in a lot of cases, but that's the kind of things that contractors are going to have to think about to adjust their mixes. All right, now we'll move on to task 6 for BMD implementation, and this is when we're getting to specifications and program development. So I'm starting to develop here. I've got all my information on the table that I just collected in task 5 and previous. I've got a bunch of data, test result experiences. Let's start writing a spec and policy. So, a couple things to think about here is certainly BMD makes you think mixed design, but there are many different ways about bringing this out to the field. So, you see some examples from the agencies that we talked to, and they run the gamut of how to handle acceptance. Some are just going on volumetric properties, and any BMD testing will be for information. Others are looking at surrogate tests. Some are looking at actual performance tests, so performing those same performance tests. And there are some small examples out there of actually paying based upon these BMD tests. Most are starting out at keeping what they already do. All right, and the frequency for BMD may not be high enough to get to the pay scale in a lot of places now, but people are working on that. Big critical item is setting the criteria. Okay, this requires input from many of the previous tasks and probably the biggest one, right? Doing your homework, benchmarking, pavement management data, production variability, your validation efforts, etc. All of those are going to feed into what is a good criteria level for your agency, for your situation, for the mix that we're talking about. Please, a note of caution here. When looking at criteria developed from other states or other research organizations, just take it with a grain of salt. It's not that it's useless, but if you're going to look at criteria like that and have it enter into your decision making, at least acknowledge and note what are the differences and conditions between that and yours. So the examples of big ones, mixed types and properties, different aggregates, different asphalt, etc. Certainly climate. Okay, there's a big difference between the NCAT test track and North Dakota. Aging conditions. How are those people or in that state handling samples, aging them, fabricating? That can lead to differences. Even their quality assurance programs. If we talk about those acceptance options, some use contractor results, some don't. Some have people at the plants, some have centralized testing. All those differences are going to feed into what their BMD spec looks like. So just acknowledge that before you kind of use it and think about it. And things to consider in task 6. It's more than just writing a spec. It's more than saying you shall meet this on X spec. It often involves doing some pilot specifications and pilot projects. Now we're moving from shadow, where everything's pretend, and we're moving into pilot specifications where it's for real, right? Contractor has to meet the test, but you're trying it on a couple projects to learn. All right, so we have some examples here where a lot of states have used them on pilot projects, test strips, field testing, those kind of things to start with. Get everybody's feet wet, see how it goes. All right. We had some that had those pilot projects optional for the contractor, where they could select whether they want to do it. Others that called it right out. Those pilot projects generally were started slow, like in the case of Illinois, where they had gradual implementation of one per district, and then they went to 2 per district, again to progress it each year. Okay, and then you take what you learn from those pilot projects, do a final analysis and specification revision, because often during the pilot projects you will learn things that maybe the original plan, maybe the original policy specification really wasn't as good as it could be, right? There are some adjustments that we need to do based upon what we learned, all right? Based upon some of what those states talked about, examples here was that some started with mixed design and then, oh, maybe we can bring it to acceptance, but maybe we need to do surrogates, okay? Or what's the differences between mixed design and production? Maybe we need to handle things differently based upon what we learned. But this really is a feedback loop that goes upon itself. So those are the things to think about in task 6 when really you get that draft of what does this BMD look like. And with that, I'll turn it over to Ellie to go into task 7.
Moving into task 7, which is concerned with developing or updating existing technician and lab qualification programs and providing training workshops on initial projects. To provide few examples related to training and certification programs, Illinois DOT and Texas DOT incorporated the mechanical tests as part of their standard technician certification program. We also heard, for instance, in the case of Caltrans, that training the contractor staff and technician on their own equipment in their own lab environment was extremely helpful. As far as lab accreditations, for instance, in Louisiana, all central labs are accredited, and district labs may be accredited as a local practice. Regardless, the technicians doing the acceptance testing are required to participate in an annual proficiency program. Moving into task 8, which is concerned with the initial implementation by state DOT of balanced mix design and mechanical testing requirements into their asphalt pavement programs. This involves developing the scope for the project selection and establishing a feedback loop to have coordinated, collaborative, and committed efforts towards a full, successful implementation of balanced mix design. So there's a need to establish the scope for project selection prior to implementation for balanced mix design. In other words, which projects are going to be selected for BMD? Is it based on the tonnage, or all the projects or all asphalt mixtures used are going to be based on the balanced mix design? Obviously, this is going to be a function of the target goals for the BMD program that were established by the state DOT. Now, also, as part of that implementation process, we saw there will be changes to the specifications and the practices. And this has become very critical to communicate those changes and new requirements to both industry and agency personnel, which can be done through webinars or face-to-face meetings and workshops, even establishing an implementation team or a task force that will help both the contractors and the state DOT personnel to address any problems that may arise during that initial implementation phase and to interpret any specification requirements. Now, throughout that process, it is critical and important to integrate a feedback loop so that the BMD specifications can be evaluated and updated regularly based on that feedback loop and the available resources. So here's an example from Illinois Department of Transportation. In 2019, they already had the Hamburg wheel tracking test implemented as part of their specs, and they were looking into the implementation of iFit. Now, they started the implementation as a phased-in implementation, where first the iFit was implemented on all interstate projects, with any additional projects approved by the central office. They ended up in total with 27 projects statewide. In 2020, the plan was now to roll out the iFit on all of their projects, all of their asphalt mixtures. However, that got postponed in order for the contractors to gain more experience and become reasonably comfortable with the mechanical test. This was all based on that feedback loop, on the contractors' feedback from the 2019 implementation. In 2021, the IFIT thresholds were implemented in both design and during productions, but that was only for short-term aged specimens because in parallel, they had some studies going on to establish the criteria for long-term aged specimens. In 2022, they rolled out the IFIT for both the short-term and the long-term aged specimens. So by 2022, now they have the Hamburg wheel tracking test implemented. They have the IFIT implemented for both design and production and after short-term aging and long-term aging conditions. So how does the mixed design and acceptance for Illinois DOT looks like? So it starts with an approach A, which is the volumetric design with the performance verifications. The contractors will conduct the lab mix design and submit the job mix formula as well as superpaved gyratory compacted specimens to the state DOT central lab for TSR testing, Hamburg wheel tracking testing, and IFIT testing. The state DOT run the test and verify the mix design for both volumetric and the mechanical testings. If everything looks good and the mix design passed the volumetric and mechanical testing requirements, then the job mix formula is approved by the state to be used in the plant. Then production can start. Then at any time, if the combined aggregate bulk specific gravity changed by more than 0.02 from the original mix design, then the contractor has to go back and then redesign the asphalt mixtures. Now, if during the productions, the first thing that the contractor has to go through is what they call a test strip, like a batch trial, if you want. That's right at the beginning of the production, and samples of asphalt mixtures are collected. They are prepared and compacted by the contractors and sent to the state district lab now for testing. And then the district lab will verify that the asphalt mixtures meet the volumetric requirements as well as the Hamburg wheel tracking test and the IFIT requirements. If everything looks good, then the mix design is verified, and then the contractors now can start the full productions. At any times, if there is failing results, right, whether for the IFIT or the Hamburg wheel tracking test during the productions, then the contractors has to implement some adjustments to their mixtures in order to have passing results. So this is basically the IDOT requirements for performance testings, which require the mechanical test on all of their asphalt mixtures, which are summarized here in these tables, including the high easel, low easel, the SMA, and the different nominal maximum aggregate size asphalt mixtures. The Hamburg wheel tracking test criteria is based on the binder performance grades, accounting for both the climate and the traffic conditions. And as you can see, the number of cycles is adjusted. The minimum number of wheel passes to 12.5 millimeter is adjusted based on the mixture type. Also, they have the IFIT requirements, and if implemented for both the short-term aging and the long-term aging, there's a different set of criteria for the different type of mixtures, and there's different set of criteria for short versus long-term aging. They also have, for moisture damage, the ASHTO T283, the indirect tensile strengths. They have a requirements for the moisture conditioned tensile strengths, the unconditioned tensile strengths, and the tensile strengths ratio. And they've separated the criteria or the requirement for the conditioned tensile strengths for polymer versus non-polymer modified asphalt binders. Now, prior to 2022 specifications, which means before the full implementation of the IFIT, the unconditioned tensile strength was capped at the 200 psi. That's to ensure that they don't have any brittle asphalt mixtures. After implementing the iFit, and specifically after implementing the iFit after long-term agings, they find out that this is not anymore necessary because the iFit should be able to eliminate those brittle asphalt mixtures. Also, after 2022 and the full implementation of the iFit, they've eliminated the VFA limits which they had on their asphalt mixtures. Following up with the IDOT examples, so when we talk to contractors about their experience with the implementation of balanced mix designs, several selected to invest in the equipment, especially those that are operating in remote areas. And in some instances, the contractors partnered in equipment purchasing and ownership. Similar to what the agencies might face in terms of lack workspace, also this can be a challenge for the contractors where they had to convert some of their storage room into a temperature control room to house the mechanical testing equipment. For instance, a contractor had to acquire interchangeable table jigs due to some space limitations in their labs. Contractors also have challenges in acquiring technicians in general, but more specifically qualified technicians to be able to run the mechanical tests. So having performance tests added to the specifications added to that challenge. Additional training on equipment and test results calculations were needed. In general, what we heard from the contractors that there was no issues or challenges in meeting the in-place density requirements. Overall, in summary, the key for success, the partnership and the continuous discussion among the different stakeholders was basically one of the key aspects for a successful implementation of balanced mix design. Following up with implementation examples is the one from Texas DOT. A flowchart here is presented according to the TxDOT specifications for mix design and mix design verifications. So starting from the top, a laboratory mix design is conducted following the volumetric requirements. TxDOT requires an approach A, which is the volumetric design with performance verifications, and the optimum binder content is selected for a 4% air voids. And then at the optimum binder content, the hammered wheel tracking test and the overlay tests are basically conducted for the design asphalt mixtures. If all the requirements are acceptable, which means the mix design passes the gradation, volumetric, and the performance test criteria, then the job mix formula is approved. Otherwise, the contractor has to go back and redesign the asphalt mixtures in a way to meet all the requirements. Now, once the job mix formula is approved, then the first step before getting into full productions is to produce a trial batch using the lab mix design, which is the job mix formula 1. And then samples are collected for the plant produced asphalt mixtures. And then again, the testing is conducted for asphalt binder content, gradation, in-place air voids, VMA, GMA, as well as the hammered wheel tracking test and the overlay test. So the produced asphalt mixtures, the trial batch from the trial batch has to meet all of these requirements. If not, then the contractors has to evaluate the trial batch and determine what changes can be done to the mixture proportions and resubmit a job mix formula 2. Now, once we have all the plant produced asphalt mixtures that meet all the requirements, then we have an approved job mix formula. At that point, then the quality acceptance criteria are being established. And what we mean by that, TxDOT is using surrogate performance tests like the ideal CT and ideal RT during productions to basically complement the mix design tests, which are the hammered wheel tracking test and the overlay test. So they need to establish a relationship between the ideal CT and the overlay test, and the relationship between the ideal RT and the hammered wheel tracking test. To do that, they use the approved job mix formula, and they go back to the lab and reproduce in the lab the asphalt mixtures at the optimum binder content plus and optimum binder content plus or minus 0.5%. So 3 different binder contents, and they establish that correlation, for instance, between the ideal CT and the overlay test, and then they translate the overlay test requirements into the ideal CT test requirement, and that becomes the acceptance limit for the ideal CT. Now, before moving any further, they validate that relationship with a plant-produced asphalt mixture. So now, during productions, they can pull out samples and run the ideal CT and run the ideal RT and check against those established acceptance limit for the ideal CT and ideal RT. So these two tests becomes used as a go no go type of test. Now, if there is any failures, they have to go back into the thrust test, which are the overlay test and the hampered wheel tracking test for evaluation. On the left-hand side, you see basically the minimum production testing frequencies. As you note that the performance testing are still being handled by the agency, in this case, the Texas DOT. Here on this slide, we have a summary of the TxDOT specifications for the various performance testing. As a little background, Texas DOT have used the balanced mix design on what they call specialty asphalt mixtures in the past, which is like, for example, the thin overlay mix or the crack attenuating mixtures. Now they're looking into expanding the use of balanced mix design on their super paved dense graded asphalt mixtures. In this table, you'll see the two tests, the requirement for the hampered wheel tracking test and the overlay test as a function of the mixture type and the high temperature asphalt binder performance grade. The requirements vary depending on the mix type. One thing here to note in the overlay test, early on, the number of cycles to failure, the minimum number of cycles to failure was the test requirements. With the work on the super paved dense graded asphalt mixtures and the balanced mix design for those mixes, they were able to go back through the historical data and establish two new test parameters, the CFE, the critical fracture energy, and the CPR, the crack propagation rate. And those are the ones that you see over here, and that's why you don't see a minimum number of cycles to failure. And to wrap up, here are some concluding comments.
Thanks, Ellie. So now we have some findings and conclusions to wrap up this webinar. A couple things that we saw, kind of universally with the case studies that were performed. Just like many changes, partnering with and collaboration between agency, industry, academia, any other stakeholders was really crucial to having successful outcomes. Having test procedures available and having that go beyond test procedures to specimen fabrication with BMD really is critical so that everyone is trying to doing it the same way as much as possible. Having some research studies to evaluate sensitivity of material properties in a given situation for a state or region. Interlaboratory studies was one of those universal things that no matter the state, no matter the situation, really find a lot of benefit out of those. It increases confidence in a given region or area between industry, academia, and agency as to these new BMD tests, what matters for variability and maybe what doesn't. Having a training program in place to, again, incorporate these new procedures and tests in so that, again, we're driving out variability by trying to do everything the same as much as possible. And then getting into shadow and pilot projects are important, but have that incremental implementation over years. And the examples that we saw of taking a step, it still took time, right? But there was progress each year, even if it wasn't major progress all the time, there was kind of this marching towards the end goal. Remember, one thing is that it's called initial implementation. So this is going to evolve. There's not going to be balloons and confetti that fall from the ceiling that say, mission accomplished, we're done. Most likely you're going to have to go back to this, continue to reevaluate, Do these tests still work over time? Check in on pilot and shadow projects over time, etc. It may be a process of BMD is implemented for a certain sector of work and you want to expand it beyond that work, maybe from high priority to the next priority of work, etc. So don't think about it as done, check mark, we're done with all this. It really is kind of needs this feedback loop to continue going and be refined. And finally, we'd just like to advertise that this material, again, was done through the Federal Highway UNR Co-op, the case studies, and this information is contained in, number one, a tech brief, all right, but also in a workshop that we offer. There's some information at the links here, and you can use the QR code to get to this flyer on the web, but we offer a one-day workshop that goes through all of these tasks in detail with examples from each of the states that we talk to on the ways to approach this. So we can do this either virtually and now in person, which we found very much effective. And this helps to kind of accomplish some of that overall planning that we talked about back in task 2 of what's the road ahead? How are we going to get this? Get on the same page as far as BMD implementation. So this is free and available to agencies and their stakeholders to do for a given region, state, agency, whatever it is. So feel free to reach out to us if you're interested in having this. And we really appreciate you listening in to the webinar to Ellie and I. So you have our thanks, and thanks for listening.